Now in this lecture we'll answer two questions. In the first question we find out here of this big rectangle EFQH, and in the second question we find out the area of this circle using two different methods. So we start with the first question. In the drawing we have rectangle EHQF. Beside this big rectangle EFQH we have three circles. The radius of this small circle is equal to 5 units in its length. The radius of this median circle is equal to 6 units in its length. The radius of this big circle is equal to 8 units in its length. Again, our test is to find out the area of this big rectangle EFQH. So first of all, we know that all the angles inside the rectangle are right angles. So those four angles are all right angles. This angle equals to 90 degrees in size. This angle is also a right angle. This is a right angle. And this is also a right angle. So here we can implement rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. For example, we have here tangent edge Q that is tangent to this median circle at this point B. The radius QB that is equal to 6. The radius QB is drawn to point B, that is the point of tendency of tangent edge Q with this median circle. And whenever your radius is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. And according to the sum rule, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. We define the point of tendency of tangent EH with this small circle. This point is point T. And we join points P and T together by a straight line. TP is the radius of this small circle, is equal to 5. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrangle EAPT we have 1, 2, 3 angles, and therefore this four pieces angle must be equal to 90 degrees in its size. According to the rule, the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle EFPT we have 4 angles. Therefore we can relate to quadrangle EFPT as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle EAPT, side PT equals to the opposite side AE. But PT is 5, therefore the opposite side EA must be also equal to 5 units in its length. We define the point of tendency of tangent EQ with this big circle. This point is point L, and we join points S and L together by a straight line. SL is of course the radius of this big circle, that is equal to 8 units in its length. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrilateral FCSL we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral EFLS we have 4 right angles, therefore according to rule 5 we can relate to this quadrilateral CFLS as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FCSL, side SL must be equal to the opposite side CF. But SL is 8, therefore the opposite side CF must be also equal to 8 units in its length. We'll define the point of tendency of tangent HQ with this big circle, this point, as point Z, and we join points S and Z together by a straight line. SZ is of course the radius of this big circle, that is equal to 8 units in its length, and according to rule 1 this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the lower quadrilateral SLQZ we have 1, 2, 3 angles, and this fourth missing angle must be equal to 90 degrees in its size. So actually this is the big angle CSZ. It is equal to 90 degrees plus 90 degrees, it is 180 degrees, and therefore CZ is a straight line because any angle that is equal to 180 degrees in its size, it is defined as a straight line. So as you know, we should find out that CZ is a straight line since line segment CZ, this is a straight line. So shape ECZ edge has 4 sides, 1, 2, 3, 4, and therefore shape ECZ edge is a quadrilateral. In quadrilateral ECZ edge we have 1, 2, 3, 4 right angles, and therefore we can relate to quadrilateral ECZ edge as a rectangle because it has 4 right angles. So can I know that quadrilateral ECZ edge is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECZ edge, side CZ must be equal to the opposite side EH. But CZ in total it is 8 plus 8, it is 16, therefore the opposite side EH must be also equal to 16 units in its length. So as you know, EH equals to 16 units in its length. In the next step, we will extend the radius BQ by a straight line until it touches side EF of this big rectangle. When you extend the straight line by straight line, the result is a straight line. Therefore, this is also a straight line. We define the tension point of the extended radius BQ with this side EF, this point is point S. So BS is a straight line. By doing this construction, you can do quadrilateral ESBH. Inside this quadrilateral ESBH, we have 1, 2, 3 angles. Therefore, this fourth missing angle must be also equal to 90 degrees in its size. So in quadrilateral ESBH we have 4 right angles, and therefore quadrilateral ESBH is a rectangle. So I denote quadrilateral ESBH is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ESBH, side ES must be equal to the opposite side SB. But EH is 16, therefore the opposite side SB must be also equal to 16 units in its length. So SB equals to 16 units in its length. In the next step, we will do a construction, that is to say, from point P, that is the center of this small circle, we will go perpendicular on SB. Again, from point P, we will go perpendicular on SB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SB this point as point X. By doing this construction, we get the name quadrilateral ASXP. Inside quadrilateral ASXP, we have 1, 2, 3 rectangles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral ASXP, we have 4 rectangles. And therefore, according to rule 5, quadrilateral ASPX is a rectangle. So I did not. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ASXP, side AP must be equal to the opposite side SX. But AP is 5, therefore the opposite side SX must be also equal to 5 units in its length. We know that SB in total equals to 16. So what is the length of this missing line segment XQ? XQ must be equal to SB minus SX minus QB. So the norm we found out that the missing line segment XQ is equal to SB minus SX minus QB. Therefore, XQ must be equal to SB is 16 minus SX is 5 minus QB is 6. So XQ in total equals to 16 minus 5 is 11, and 11 minus 6 is 5. So if you found out that the missing 97 XQ equals to 5 units in its length. In the next step, we join points P and Q together by a straight line. Point P is the center of the small circle, point Q is the center of this medium circle. So PQ is the distance between their centers. Here PQ is the distance between the center of this small circle and the center of this medium circle. And here we can implement rule 10 because we have an external lash between the small circle and the medium circle. That is to say, they touch each other externally in this point. So we define the touching point. This point is point Y. Whenever we have an external lash between two circles, like in this drawing, we can implement rule 10. So repeat quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. In the drawing, we have two circles. The center of this circle is at point O. The center of this circle is at point M. They touch each other externally at this point, point K. The straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point K. Again, the straight line OM must pass through point K, that is their touching point. Or OKM is one straight line. Again, OKM is one straight line according to this rule 10. So we can implement rule 10 in our drawing, because in our drawing, those two circles have an external lash between them at point Y. The center of this circle is at point P. The center of this medium circle is at point Q. And the straight line that connects their centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through their touching point, that is point Y. Again, the straight line PQ must pass through point Y, that is their touching point. Or PYQ is one straight line. Again, PYQ is one straight line, according to rule 10. PY is the radius of this small circle, that is equals to 5. QY is the radius of this medium circle, that is equals to 6. And because of the fact that according to rule 10, PYQ is one straight line, it means that PQ must be equal to PY plus YQ. Again, PQ must be equal to PY plus YQ. So PQ in total must be equal to PY, that is 5, plus YQ, that is 6. So in total, PQ must be equal to 5 plus 6, that is 11. So PQ equals to 11 units in its name. In the next step, I'll copy the right green triangle PXQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PXQ. According to the Pythagoras theorem, in a right triangle, the square of the opposite equals to the sum of the squares of the perpendiculars. Here by PT is the perversion for Pythagoras theorem. So actually, this is the right green triangle PXQ that I copied from the original drawing. It is right triangle PXQ according to the Pythagoras theorem. PQ squared PQ equals to 11 units in its length. And XQ equals to 5 units in its length. According to the Pythagoras theorem, this right triangle pxq, pq squared, that is the square of the hypotenuse, must be equal to px squared plus xq squared. So write it down. pq squared, that is the square of the hypotenuse, equals to px squared plus xq squared. PQ is 11, therefore PQ squared is 11 squared, that is 121, and it is equals to PX squared. PX is the missing side, so we leave it as it is, so it is PX squared plus XQ squared. XQ is 5, therefore XQ squared is 5 squared, that is 25. So in total we should find out that 121 equals to PX squared plus 25. Here we subtract 25 from this equation, and we get that 121 plus 25 is 96, so 96 equals to px squared. Here we substitute 96 by 16 times 6, so we found out that 16 times 6 equals to px squared. Here we take a root out of this equation, and finally we get that the missing side px equals to the square root of 16 times 6. The square root of 16 is 4, so inside the root we left only with 6. So she found out that the length of the missing 9 segment px is equal to 4 times square root of 6 units in its length. This is the missing 9 segment px, that is equal to 4 times square root of 6 units in its length. We have already found out that the small quadrangle APXS is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle APXS, side PX must be equal to the opposite side AS. But PX is 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units in its length. In the next step, we'll join points Q and S together by third line. Point Q is the center of this medium circle. Point S is the center of this big circle. So actually QS is the distance between their centers. Here we can implement rule 10 because we have an external between those two circles at this point. We will define the touching point, this point, as point G. According to rule 10, the center of this medium circle is at point Q, the center of this big circle is at point S, and the third line that connects the centers together is of course the third line QS. And according to rule 10, the third line QS must pass from point B, that is the touching point, or QGS is one third line. Again, QGS is one third line. QG is the radius of this medium circle, that is equals to 6 units in its length. SG is the radius of this big circle, that is equal to 8 units in its length. Therefore, QS must be equal to QG plus GH. Again, QS must be equal to QG plus GH plus GS because QGS is one third line. So QS in total must be equal to 6 plus 8, that is 14. QS equals to 14 units in its length. So it is known QS equals to 14 units in its length. In the next step, we will do a construction, that is to say, from point Q, that is the center of this medium circle, we will do a perpendicular on CZ. And from point Q, we will do a perpendicular on CZ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CZ. This point is point J. So we have here quadrilateral QJZB. Inside this quadrilateral QJZB, we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Quadrilateral QJZS is 4 right angles, and therefore it is a rectangle. So it is known, this is quadrilateral QJZB, this is a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle QJZB, side QB must be equal to the opposite side JZ. But QB is 6, therefore the opposite side ZJ must be also equal to 6 units in its length. So what is the length of this missing short line segment SJ? SJ equals to SZ minus JZ. Again, SJ equals to SZ minus JZ. So it is known, if you found out that SJ equals to SZ minus JZ. So SJ equals to SZ is the radius of this big circle, that is 8, minus JZ, that is equals to 6. 8 minus 6 is 2. Therefore, SJ equals to 2 units in its length. In the next step, I'll copy the right green triangle QSJ in a new page, and we will implement the Pythagoras theorem on this green right triangle QSJ. Here by PT is the progression of Pythagoras theorem. Actually, this is the right green triangle QSJ, that is coming from the original drawing. Side SJ equals to 2 units in its length, and the opposite SQ equals to 14 units in its length according to rule 10. This right triangle QSJ, SQ squared, that is the square of the hypotenuse, equals to SJ squared plus JQ squared. So it is known QS squared, that is the square of the hypotenuse, equals to SJZ, SJ squared, plus QJ squared. QS, the hypotenuse QS is 14, therefore QS squared is 14 squared, that is 196, and it is equal to SJZ. SJ squared, SJ is 2, therefore SJ squared is 2 squared, that is 4, plus QJ squared. QJ is the missing sign, so we leave it as it is. So this is QJ squared. So in total, if you found out that 196 is equals to 4 plus QJ squared. Here we subtract 4 from this equation, and we get that 196 minus 4 is 192 equals to QJ squared. We substitute 192 by 64 times 3, so 64 times 3 equals to QJ squared. Here we take a root out of this equation, and finally we get that the missing 97 QJ is equal to the square root of 64 is 8, so inside the root we left only with 3. So total we found out that the missing 97 QJ is equal to 8 times square root of 3 units in its length. This is the missing 97 QJ is equal to 8 times square root of 3 units in its length. Inside quadrilateral CJQS, we have 1, 2 right angles. We know that EF is one side of rectangle EFQH, therefore it is absolutely a straight line. So if we focus on the lower side of the straight line EF at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line EF at point S? We have this angle that is 90 degrees, plus this missing angle. In total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So inside quadrilateral SCJQ we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Inside quadrilateral SCJQ we have 4 rectangles, and therefore quadrilateral SGJQ is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So rectangle SCJQ, side QJ must be equal to the opposite side SC. But QJ is 8 times square root of 3, therefore the opposite side SC must be also equal to 8 times square root of 3 units in its length. So if we found out that side EF in total equals to 5, plus 4 times square root of 6, plus 8 times square root of 3, plus 8. So the length is the sum of those four numbers, the length of rectangle EFQH, and the width is EH is equal to 16, and the area of this big rectangle EFQH is the width times the length. So it is done. We should find out that the area of this big rectangle EFQH is equal to the width of the rectangle times the length. And again, the length of the rectangle EFQH equals to the width of the rectangle times the length. The width of this big rectangle EFQH is EH. and the length is EF. The length is EF. So in total we have found out that the area of an EFQH equals to EH times EF. The width EH is 16 and the length EF is EA plus AS plus SC plus CF. And again, the area of EFQH equals to the width that is 16 times the length that is EA plus AS plus SC plus CF. So it is 16 times EA. EA is 5 plus AS. AS is 4 times 4 to 6 plus SC. SC is 8 times 4 to 3 plus CF, that is 8. So total, if you want out that the EFQH equals to 16 times 5 plus 4 times 4 to 6 plus 8 times 4 to 3 plus 8. Actually, the value of this expression in total, it is equal to 586.47 square units in its size. So if we found out that the area of this big rectangle, EFQH, that is the area that we are looking for this question, is equal to 586.47 square units in its size. So if we finish with the first question, in the next step I will present you the second question and we will solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. So in the domain we have a circle. This is called AB, that is equals to 8 units in its length. This is called PQ, that is equals to 6 units in its length. This is again PMQ, that is a right angle. Again, our task is to find out the area of this circle. So the first step, I will present to you Rule 29 and we will implement Rule 29 in our drawing. According to Rule 29, peripheral angles that subtend on the same arc are equal to each other. So in the drawing we have a circle. This is peripheral angle BAC. This is equal to alpha degrees in its size. And peripheral angle BAC. This is peripheral angle BDC. This is equal to alpha degrees in its size, and peripheral angle BDC subtend on arc BC. Again, peripheral angle BDC subtend on arc BC. Likewise, this is peripheral angle BEC. This is equal to beta degrees in its size, and peripheral angle BEC subtend on the same arc BC. And because of the fact that those two peripheral angles are both subtend on the same arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So according to this Rule 29, if two peripheral angles subtend on the same arc, they must be equal to each other in their sizes. So we can implement Rule 29 in our drawing. Why? Because in our drawing, if we focus on this arc BQ, this is arc BQ. The red curve is arc BQ. this is perpendicular BAQ that subtend on arc BQ. Likewise, this is perpendicular BPQ that subtend on the same arc BQ. And because of the fact that those two perpendiculars they are both subtend on the same arc BQ, they must be equal to each other in their sizes. So if we define the size of this perpendicular BAQ as alpha, then the size of this perpendicular BPQ must be also equal to alpha, because they are equal to each other according to rule 29. In the next step, we'll focus on this arc AP. This is arc AP. This is angle perpendicular AQP. Perpendicular AQP subtend on arc AP. Likewise, this is perpendicular ABP. That's subtend on the same arc AP. And because of the fact that those two perpendiculars are both subtend on the same arc AP, they must be equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to rule 29. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in size, because they are equal to each other. So in the right triangle A and B, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle A and B? Angle alpha plus angle beta plus 90 degrees, in total they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So alpha plus beta plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. Here we multiply this equation by 2, and finally we get that 2 alpha plus 2 beta equals to 180 degrees. And again, we found out that 2 alpha plus 2 beta equals to 180 degrees. In the next step, I present to you rule 13, and we implement rule 13 in our drawing. According to rule 13, a certain angle is twice as large as the perpendicular subtended on the same chord. Repeat again. A certain angle is twice as large as the perpendicular subtended on the same chord. In the drawing, we have a circle. This is perpendicular ACB. This equals to theta degrees in size. This is a certain angle AOB, and perpendicular ACB subtend on arc AB. Therefore, according to this rule 13, certain angle AOB that subtend on the same chord AB must be twice as large as this perpendicular ACB. Perpendicular angle ACB equals to theta, therefore certain angle AOB must be equal to 2 theta. So center angle is twice as large as the peripheral angle that subtend on the same chord. So we can implement rule 13 in our drawing. We define the center of this circle, this point is point O, and we draw center angle AOP. This is center angle AOP that subtend on chord AP. Again, center angle AOP subtend on chord AP. But peripheral angle AQP also subtend on chord AP. And according to rule 13, the size of peripheral angle AOP must be twice as large as the size of peripheral angle AQP that subtend on the same arc AP. The size of peripheral angle AQP is better, therefore the size of center angle AOP must be equal to 2 beta, according to rule 13. In the next step, we create another center angle, BOQ. This is center angle BOQ that subtend on chord BQ. Again, center angle BOQ subtend on chord BQ. Again, center angle BOQ subtend on arc BQ. But peripheral angle BAQ subtend on the same arc BQ. Therefore, center angle BOQ must be twice as large as peripheral angle BOQ that subtend on the same arc BQ. Center angle peripheral angle BAQ equals to alpha, therefore center angle BOQ must be equal to 2 alpha, according to rule 13. In the next step, we define angle QOP. This angle is angle X. And we define angle AOB. This angle is angle Y. We have the rule that says that the sum of the angles around any point is equal to 360 degrees. Again, the sum of the angles around any point equals to 360 degrees. So the sum of the angles around point O must be equal to 360 degrees. So which angles we have around point O? We have 2 alpha plus 2 beta plus x plus y. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that I mentioned. The sum of the angles around any point is equal to 360 degrees. So 2 alpha plus 2 beta plus x plus y equals to 360 degrees. But we already found out that 2 alpha plus 2 beta equals to 180 degrees. Therefore, we can substitute 2 alpha plus 2 beta in this equation by 180 degrees. So we get that 2 alpha plus 2 beta is 180 degrees plus x plus y. In total, it must be equal to 360 degrees. Here we subtract 180 degrees from this equation, and we get that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. So if we found out that x plus y equals to 180 degrees, In the next step, I'll present to you Rule 30 and we'll implement Rule 30 in our drawing. According to Rule 30, central angles that subtend on equal chords are equal to each other. In the drawing we have a circle. This is central angle COD. The size of this central angle AOD is alpha degrees. Central angle COD subtend on chord CD. Likewise, this is central angle AOB. The size of central angle AOB is beta. Central angle AOB subset on RKB. According to this rule 30, if chord AB equals to chord CD, then those two perpendicular angles must be equal to each other in their sizes. That is to say, if chord AB equals to chord CD, then alpha equals to beta. Again, if chord AB equals to chord CD, then those two perpendiculars must be equal to each other in their sizes. That is to say, alpha equals to beta. So we can actually implement Rule 30 in our drawing. In our drawing, we have central angle POQ that is equals to x degrees in its size. Central angle POQ subtend on chord PQ. The length of chord PQ is 6 units. And we have central angle AOB that is equals to y degrees in its size, and it's subtend on chord AB. So I'll copy this circle in a new page, and we will implement Rule 30 in this circle. Point O is the center of the circle. So actually, I copied this circle here. Then don't look exactly with the same size, but we actually relate to those two circles that are equal to each other in their sizes. And the center of this circle is here at point O. I copy chord AB in the new circle. Chord AB equals to 8 units in its length. And peripheral central angle AOB equals to y degrees in its size. In the next step, we will do a construction. First of all, this is central angle AOB. This is equals to y degrees in its size, and central angle AOB subtend on chord AB. This is equals to 8 units in its length. In the next step, I will draw a chord, and the length of the chord will be equal to 6 units in its length. This is chord BC, and according to our construction, chord BC equals to 6 units in its length. In the next step, we join points O and C together by a straight line. By doing this construction, we created center angle BOC. center angle BOC subtend on chord BC that is equals to 6 units in its length. Again, center angle BOC subtend on chord BC that is equals to 6 units in its length, and those two circles are identical. Here we have center angle POQ that subtend on arc PQ that is also equals to 6 units in its length, and the size of center angle POQ is x. Therefore, the size of this center angle BOC must be also equal to x because they both subtend on equal arcs. They both subtend on arcs that their length is 6 units. Center angle POQ subtend on arc PQ that is equals to 6 units in its length. Center angle COB also subtend on arc CB that is also equals to 6 units in its length, and therefore according to rule 30, if center angles subtend on equal arcs like here, they must be equal to each other in their sizes. But the size of this center angle is x, therefore the size of this center angle COB must be also equal to x degrees because it's subtend on equal arcs. On chord BC is equals to 6 units in its length, exactly like this center angle POQ that is also subtend on arc PQ that is equals to 6 units in its length, and therefore according to rule 30, if center angles subtend on the same chords, on equal chords, they must be equal to each other in their sizes. The size of this center angle POQ is x, therefore the size of this center angle COB must be also equal to x because they both subtend on equal arcs, that is 6 units. So we actually found out that angle AOC equals to x plus y degrees in its size. This is the big angle AOC that is equals to y plus x, or x plus y degrees in its size. But we have already found out that x plus y equals to 180 degrees. Therefore, angle AOC equals to x plus y, that is 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. Therefore, AC is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes through the center of the circle is the diameter of the circle. Therefore, AC is the diameter of the circle. AC is the diameter of the circle. So I write it down. This is called AC. That is the diameter of this circle. So here we can implement rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is peripheral angle ACB that subtend on AB, that is the diameter of the circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size. So we can definitely implement Rule 7 in our drawing. Why? Because in our drawing we have peripheral angle ABC that subtend on chord AC, that is the diameter of the circle, and therefore according to Rule 7, peripheral angle ABC must be equal to 90 degrees in its size. This is the right angle according to Rule 7. In the next step, we'll implement the Pythagoras theorem on this right angle, triangle ABC. So copy the right angle ABC in the new page, and we will implement on it the Pythagoras theorem. Side AB equals to 8 units in its length, side BC equals to 6 units in its length according to our construction, and AC is the diameter of the circle. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle ABC, this is the code from the original drawing. This right triangle ABC according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So write it down. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so we'll leave it as it is. So it is AC squared equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So total we found out that AC squared equals to 64 plus 36. 64 plus 36 is 100. Here we take a root out of the equation and find that the diameter AC of the circle is equal to 10 units in its length. If the diameter AC is 10, then the radius is 5. So the radius R equals to 5. It is half of the diameter. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total, the area of our circle is equal to either 25 pi square units in square units in its size. In terms of numbers, it is equals to 78.54 square units in its size. Okay, again, we should find out that the area of the circle that we are looking for, that is the area of this circle, it is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use some of the things that we already found out in the first method. In the first method, we already found out that those values are both equal to alpha. Those vertex areas that are equal to each other, therefore this area must be equal to 90 degrees in its size. So in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you prove that all the angles of this right triangle MPQ are corresponding equal to all those angles of the right triangle A and B. Therefore, those two right triangles are similar to each other according to angle similarity rule. So write it down. If you found out that the right triangle A and B is similar, this is the sign of similar, to the right triangle PMQ, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle A and B over side PQ of the right triangle PMQ is equal to side AM of the right triangle A and B over side PM of the right triangle PMQ, and it is also equal to side MB of the right triangle A and B over side MQ of the right triangle PMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive the side AB of the right triangle A and B over side PQ of the right triangle PMQ is equal to side AM of the right triangle A and B over side PM of the right triangle PMQ, and it is also equal to side MB of the right triangle A and B over side MQ of the right triangle PMQ. AB is 8 over PQ. PQ is 6. So 8 over 6 equals to AM over PM. Here we divide both the numerator and the numerator of this number by 2, and we get that 8 over 2 is 4 and 6 over 2 is 3. So 8 over 6 equals to 4/3. And this is equals to AM over PM. Here we multiply both the numerator and the denominator of this number by A. We get that 4A over 3A equals to AM over PM. A over A is 1, and it is allowable to multiply any expression by 1. Will not change the value of the expression. So if we found out that 4A over 3A equals to AM over PM, those two sides of the equation are equal to each other, and therefore the numerator of this side of the equation must be equal to the numerator of this side of the equation. That is to say, if we found out that AM equals to 4A, likewise, the denominator of this on this side of the equation must be equal to the denominator of this side of the equation. This is to say, PM equals to 3A. PM equals to 3A. We actually found out that AM, this is side AM, this is equals to 4A. This is side PM, that is equals to 3A. We continue to focus on the long equation. Those two sides are equal to each other. AB over PQ is 4/3. So 4/3 equals to MB over MQ. Again, 4/3 equals to MB over MQ. So it is not. 4/3 equals to MB over MQ. Here we will multiply both the numerator and the denominator of this number by B, and we get that 4B over 3B equals to MB over MQ. Those two sides of the equation are equal to each other, and therefore the numerator of this side of the equation must be equal to the numerator of this side of the equation. So this is to say, 4B must be equal to MB, and 3B must be equal to MQ. So if you found out that MB equals to 4B and MQ equals to 3B. MB equals to 4B. And MQ equals to 3B. The next step, we join points B and Q together by step 9. We know that PB is a chord, and PB is a chord, it is absolutely straight line. So if you focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Wolfrid said that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PB at point M? We have this angle, this is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Wolfrid. Therefore, this missing angle must be equal to 90 degrees in its size. So we have here the right angle MBQ. So copy the right angle MBQ in your page, and we will implement the Pythagoras theorem on this right angle MBQ. Here by PT is the abbreviation for Pythagoras theorem. Side MB equals to 4B units in its length. And side MQ equals to 3B units in its length. So actually, this is the right angle BMQ that are coming from the original domain. This right angle BMQ according to the Pythagoras theorem, BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. So write it down. BQ squared, that is the square of the hypotenuse, is equal to MB squared plus MQ squared. BQ is the missing side, so we remove the CT, so it is BQ squared. That is equal to MB squared. MB squared, MB is 4B, therefore MB squared is 4B squared. 4B squared is 16B squared. 16B squared plus MQ squared. MQ is 3B, therefore MQ squared is 3B squared, that is 9B squared. So in total, we should know that BQ squared equals to 16B squared plus 9B squared is 25B squared. So we should know that BQ squared equals to 25B squared. Here we'll take a root out of this equation and find that BQ equals to the square root of 25 is 5 times the square root of B squared is B. So in total we found out that the length of the missing side, that is the hypotenuse BQ, is equals to 5B units in its length. This is line segment BQ is equals to 5B units in its length. In the next step, we calculate the area of this triangle ABQ in two different ways, and we create an equation that says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method of calculation. Okay, so in the first method, we will calculate the area of triangle ABQ according to the formula that the area of any triangle is equal to the base of the triangle times the height to the base over 2. We choose the base of triangle ABQ as AQ times the height to the base, that is BM, because it's greater than 90 degrees of the base AQ, over 2. So according to the first method, there of this triangle ABQ equals to AQ, that is the base of the triangle, times BM, that is the height to the base, over 2. And it must be equal to the outer ABQ if we calculate the of this triangle ABQ according to the second method. We use the formula that said that this is a triangle ABC that could be any triangle. Side AB equals to A unit in itself, side AC equals to B unit in itself, and side BC equals to C unit in itself. This is angle BAC that is equal to 30 degrees in size. So this triangle ABC that could be any triangle, there of this triangle ABC is equal to A times B times sinus theta over 2. Again, there of triangle ABC equals to A times B times sinus theta over 2. Or in other words, the of any triangle is equal to the multiplication of the two sides by each other times the angle between the two times sinus the angle between times sinus the angle that is between those two sides. Again, it is the multiplication of two sides by two sides by each other times sinus the angle that is between those two sides. This is angle that is sinus theta over 2. So we use the new formula in order to find out the of this triangle ABQ. So it will be equal to side AB times side BQ times sinus the angle between the two sides. Times sinus the angle between the two sides, AB and BQ. The angle between side AB and BQ is angle ABQ. So it is times sinus angle ABQ divided by 2. So thereafter angle ABQ according to the first calculation must be equal to thereafter angle ABQ according to the second calculation or the second method. We have to find out the value of sinus angle ABQ. In order to find out of the value of sinus ABQ, we use the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. The law of side AB is C units, side AC equals to B units in itself, and side BC equals to A unit in itself. This is angle alpha, this is angle beta, and this is angle gamma. According to the law of sines, the following equation is true, that A over sinus alpha equals to B over sinus beta equals to C over sinus gamma, and it is equals to 2R. R is the radius of the circle that blocks triangle ABC. Again, R is the radius of the circle that blocks triangle ABC. And therefore 2R is the diameter of the circle that blocks this triangle ABC. We can definitely implement all the law of sines in our drawing. Why? Because in our drawing we have a triangle ABQ that is blocked by this circle. Or this circle blocks triangle ABQ. Therefore, we can definitely implement the law of sines in this triangle ABQ. According to the law of sines, the following equation will be 2. That AQ over sinus angle ABQ equals to 2R. Again, AQ over sinus angle ABQ equals to 2R. And R is the radius of this circle that blocks triangle ABQ. So according to the law of sines, the following equation is true. If we relate to triangle ABQ, the following equation will be true according to the law of sines. AQ over sinus angle ABQ equals to 2r. And 2r is the diameter of this circle that blocks triangle ABQ. Because again, according to the law of sines, the following equation is true. If we relate to triangle ABQ that is blocked by this circle, the following equation is true that AQ over sinus angle ABQ equals to 2r, and 2r is the diameter of this circle that blocks this triangle ABQ. Actually, this equation is the implementation of the law of sines in our drawing. If we relate to triangle ABQ, here we will multiply this equation by sinus angle ABQ, and we divide it by 2r in order to find out the value of sinus angle ABC. And we get that sinus angle ABQ, this angle ABQ, is equal to AQ over 2r. Repeat again. We multiply this equation by sinus angle ABQ, and we divide it by 2r simultaneously, and found out actually that sinus angle ABQ equals to AQ over 2r. Therefore, we can substitute sinus angle ABQ in this equation by AQ over 2r. We'll do it now, and we get that AQ times BM over 2 equals to AB times BQ over 2, and sinus angle ABQ equals to AQ over 2r. So after we substitute sinus angle ABQ by AQ over 2r, we got this equation that AQ times BM over 2 equals to AB times BQ over 2 times AQ over 2r. Here we have 2 on both sides of this equation, so 2 will get cancelled. We have AQ on both sides of this equation, so AQ also will get cancelled. After we cancel those two expressions, we left only, in this side of the equation, we left only with BM. This equals to AB times BQ over 2r. Here we will multiply this equation by r, and we divide it by BM simultaneously in order to find out the value of r. And we get that r equals to AB times BQ over 2 times BM. So r equals to AB AB is 8 times BQ. BQ is 5B. Over 2 times bm. bm is 4b. We have 8 in the numerator, and 2 times 4 is 8. So we have 8 also in the denominator. So 8 we cancel with 8. B over B is 1. So B also gets cancelled. And we found out that R equals to 5 units in its length. Our task is to find out the area of this circle. So we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. So it is pi times r squared. R is 5, therefore r squared is 5 squared, this is 25. So if you found out that the area of this circle, this is the area that we are looking for in this equation, this is equals to 25 pi square units in size, so in terms of numbers, this is equals to 586.47 square units in its size. So in both methods, we found out that the area of this circle is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle equals to 586.47 square units in its size. So we finish with the second method of the second question. In the next step, so the next step, we'll start with the first question, of course. The first question, our test is to find out the area of this big rectangle AFQH. So in the drawing we have the big rectangle AFQH. Inside this big rectangle we have 3 circles. The radius of this small circle is equal to 5 units, the radius of this medium circle is equal to 6 units in its length, and the radius of this big circle equals to 8 units in its length. Again, our test is to find out there of this big rectangle EF QH. So first of all, we know that all the angles inside the rectangle are right angles. So those 4 angles, they are all right angles. We implemented here rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So for example, we have here the medium circle, the radius QB is equal to 6. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever your radius that is drawn to the point of tendency, then tangent AQ will be perpendicular to the radius BQ. If AQ is perpendicular to BQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. According to rule 1, those two angles are both right angles. Likewise, according to rule 1, those two angles are also right angles. Those two angles are also right angles. And those two angles are also right angles. We join points S and 2 together by a straight line. This is the radius. So those two angles are also right angles. And again, those two angles are also right angles according to rule 1. So we have here the big quadrilateral. Before that, we have here this is line segment CZ, and here we have quadrilateral CFLS. Beside this quadrilateral CFLS, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. Likewise, the lower quadrilateral SLQZ, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. So this is the big angle CSZ, that is equal to 180 degrees in its size, and therefore we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore CZ is a straight line. CZ is a straight line. So this shape CZ edge E, it has 4 right angles, 4 sides, 1, 2, 3, 4, and therefore this shape ECZ edge is a quadrilateral. So it has 4 sides. Inside this quadrilateral ECZ edge, we have 4 right angles, 1, 2, 3, 4. And therefore quadrilateral ECZ edge is a rectangle. Quadrilateral ECZ edge is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ECZ edge, side CZ must be equal to the opposite side EH. But CZ in total equals to 8 plus 8, that is 16. Therefore the opposite side EH must be also equal to 16 units in its length. In the next step, we extended the radius BQ by straight line until it touches side EF at this point, point S. By doing this construction, we can do quadrilateral SE edge B. Inside this quadrilateral SE edge B, we have 1, 2, 3, 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SE edge B, side SB must be equal to the opposite side EH, but EH is 16, therefore SB must be also equal to 16 units in its length. SB equals to 16 units in its length. In the next step, we joined from point P, we go perpendicular on SB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P, and side SB, this point is point X. By doing this construction, we get the quadrilateral AS XP. Inside quadrilateral AS XP, we have 1, 2, 3 angles, and therefore this 4 piece angle must be equal to 90 degrees in each side, and therefore quadrilateral AS XP is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AS XP, side AP must be equal to the opposite side SX. But AP is 5, therefore the opposite side SX must be also equal to 5 units in its length. Side QB equals to 6 units in its length, and SB in total equals to 16. Here SB equals to 16. So what is the rough of this missing line segment SQ? SQ equals to SB minus SX minus QB. XQ equals to SB minus SX minus QB. So XQ equals to SB, that is 16, minus SX, that is 5, minus QB, that is 6. 16 minus 5 minus 6 is 5. So XQ equals to 5 units in its length. In the next step, we join points P and Q together by straight line. We have an external knot between those two circles, that is to say that touch each other externally is point Y, and therefore we can implement the rule 10. According to rule 10, the straight line that connects the centers together, that is the straight line PQ, must pass through point Y, that is their touching point. Or PYQ is one straight line. PYQ is one straight line, and therefore PQ must be equal to PY, that is 5, plus YQ, that is 6. The above the area of those circles, therefore the radius of this circle is 5, and the radius of this circle is 6. So PQ equals to 5 plus 6, that is 11. In the next step, I copied the right green triangle PXQ in a new page, and we implemented the also on this right green triangle PXQ. So here, this is the right triangle PXQ that I copied from the original drawing. In this right triangle PXQ, PQ squared, that is the square of the hypotenuse, equals to PX squared plus XQ squared. PQ is 11, therefore PQ squared is 11 squared, this is 121, and this is equals to PX squared. PX is the missing sign, so we leave it as it is, plus XQ squared. XQ is 5, therefore XQ squared is 5 squared, that is 25. So in total we should find that 121 equals to PX squared plus 25. Here we subtract 25 from this equation, and we found out that 121 minus 25 is 96. So 96 equals to PX squared. Here we substituted 96 by 16 times 6, so 16 times 6 equals to Px squared. Here we took out of this equation, and we found out that Px equals to the square root of 16 times 6. The square root of 16 is 4, so inside the root we left only 6. So in total we should find out that Px equals to 4 times square root of 6 units in its length. This is line segment Px. This is line segment Px. Actually, this is line segment Px. Is equals to 4 times square root of 6 units in its length. The quadrilateral ASXP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ASXP, side PX equals to the opposite side AS. But PX is 4 times square root of 6, therefore the opposite side AS must be also equal to 4 times square root of 6 units in its length. In the next step, we join points Q and S together by straight line. Point Q is the center of the medium circle, and point S is the center of this big circle. Those two circles have an external knot between them at point G. Therefore, according to rule 10, the straight line that connects the centers together, this is to say the straight line QS must pass from point G, that is the touching point, or QGS is one straight line, If QGS is 1 cent line, then QS in total must be equal to QG, that is 6, plus GS, that is 8. 6 plus 8 is 14, so QS in total equals to 14. In the next step from point Q, we do perpendicular on CZ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CZ. This point is point J. By doing this construction, we get the quadrilateral QJZB. Inside quadrilateral QJZB, we have 1, 2 right angles, and therefore this 4 pieces must be equal to 90 degrees in its size. Therefore, quadrilateral QJZB is a rectangle, and you know that the opposite sides of the rectangle are equal to each other. That is to say, in rectangle QJZB, side QB must be equal to the opposite side JZ. But QB is 6, therefore the opposite side JZ must be also equal to 6 units in its length. So what is the length of this short line segment SJ? SJ equals to SZ minus JZ. Again. Sj equals to Sz, that is 8, minus Jz, that is 6. 8 minus 6 is 2. So Sj equals to 2 units in its length, and the opposite Qs equals to 14 units in its length. In the next step, I copy the right green triangle QSJ in a new page and implemented the Pythagoras theorem on this right triangle, triangle QSJ. So this is the right triangle QSJ that I copied from the original domain. In this right triangle QSJ, QS squared, that is the square of the hypotenuse, equals to Sj squared plus Jq squared. QS is 14, therefore QS squared is 14 squared, it is 196, and it is equals to Js squared. Js is 2, therefore Js squared is 2 squared, it is 4, plus Qj squared. Qj is the missing side, so it is. So 196 equals to 4 plus Qj squared. Here substitute 4 from this equation, and I found out that 196 plus 4 is 192 equals to Qj squared. 192 is 64 times 3, so 64 times 3 equals to Qj squared. Here we took out for this equation, and finally found out that Qj equals to the square root of 64 is 8, so inside the root we left only 3. So in total we found out that the missing side Qj equals to 8 times square root of 3 units in its length. This is the missing side Qj, that equals to 8 times square root of 3 units in its length. On the other, SQJC is a rectangle because it has 4 rectangles. And we know that the opposite sides of a rectangle are equal to each other. So in rectangle SCJQ, side QJ must be equal to the opposite side SC. But QJ is 8 times square root of 3, therefore the opposite side SJ, the opposite side SC must be equal to 8 times square root of 3 units in its length. So we know that the length of the EF is equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8, and the width edge is 16. Therefore, in total, the area of the EFQ edge is equals to the width of the rectangle times the length. The width is the edge and the width is the EF. And the width is the edge and the width is the EF. EH is 16 and EF in total equals to EA plus AS plus SC plus CF. So total area of rectangle EFQH equals to 16, and times EA is 5 plus AS is 4 times square root of 6 plus SC is 8 times square root of 3 and CF is 8. So the value of this expression is 586.47 square units in size. So if you found out that there are this big rectangle AFQH is equal to 586.47 square inches in its size. So we finish with the first question, and the next step I presented to you the second question, and we solve the second question by using two different methods. Our task in the second question is to find out the area of this circle. So in the drawing we have a circle. This is called AB, that is equal to 8 units in its length. This is called PQ, that is equal to 6 units in its length. This is angle PMQ, that is the right angle. Again, our task is to find out the area of this circle. So first of all, I presented to you all 29, and we presented all 29 in our drawing. According to all 29, three triangles that subtend on the same arc are equal to each other. In the drawing we have a circle. This is triangle BDC. This is equal to alpha degrees in its size, and triangle BDC subtend on arc BC. Again, triangle BDC subtend on arc BC. Likewise, this is triangle BEC. This is equal to beta degrees in its size, and triangle BEC subtend on the same arc BC. And because of the fact that those two triangles subtend on the same arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So according to this rule 29, if two triangles subtend on the same arc, they must be equal to each other in their sizes. We can implement rule 29 in our drawing. Because in our drawing we have triangle BAQ that subtend on arc BQ. Likewise, we have triangle BPQ that is also subtend on the same arc PQ. And because of the fact that those two triangles subtend on the same arc PQ, they must be equal to each other in their sizes according to rule 29. So if this triangle is equal to alpha degrees in its size, then this triangle BPQ must be also equal to alpha degrees in its size, because they are equal to each other according to rule 29. Likewise, if we focus on this arc AP, we have triangle ABP that subtend on arc AP. Likewise, this is triangle AQP that is also subtend on the same arc AP. And because of the fact that those two triangles subtend on the same arc AP, they must be equal to each other in their sizes. So if the size of this triangle is better, then the size of this triangle must be also equal to beta, because they are equal to each other according to rule 29. In the next step I presented to you rule 13, and we implemented rule 13 in our drawing. According to rule 13, a center angle is twice as large as the triangle subtended on the same chord. In the drawing we have a circle. This is triangle ACB that subtend on chord AB. The size of triangle ACB is theta. This is a center angle AOB that subtend on the same arc AB. And therefore, according to this rule 13, the size of center angle AOB must be twice as large as the size of triangle ACB, well, because they both subtend on the same chord called AB. But the size of triangle ACB is theta, therefore the size of center angle AOB must be equal to 2 theta, according to this rule 13. So according to rule 13, the size of a triangle must be twice as large as the size of, again, the size of the center angle must be twice as large as the size of the triangle that subtend on the same chord. So you can implement on the same chord or the same arc, it doesn't matter. So we can implement rule 13 in our drawing. In our drawing, I draw center angle AOP that subtend on arc AP. We have peripheral angle ABQ that subtend peripheral angle AQP that subtend on the same arc AP. The size of peripheral angle AQP is better, therefore the size of center angle AOP that subtend on the same arc AP must be equal to 2 beta. Likewise, I draw center angle QOB that subtend on arc BQ. But we have peripheral angle QPB that subtend on the same arc QB. And the size of peripheral angle QPB is alpha, therefore the size of center angle QOB that subtend on the same arc QB must be equal to 2 alpha, according to rule 13. In the next step, I define this angle QOP as x and this angle AOB as y. And we know that the sum of the angles around any point is equal to 360 degrees. And therefore the sum of the angles around point O, that is the center of this angle, must be equal to 360 degrees. So each angles we have around point O, we have 2 alpha plus 2 beta plus x plus y equals to 360 degrees. So if we focus at point O, the sum of the angles at point O must be equal to 360 degrees. In total, around point O, we have 4 angles, 2 alpha plus 2 beta plus x plus y must be equal to 360 degrees. But we have already found out that 2 alpha plus 2 beta equals to 180 degrees, therefore we can substitute 2 alpha plus 2 beta by 180 degrees, and we get that 2 alpha plus 2 beta is 180 degrees, plus x plus y equals to 360 degrees. We subtracted 180 degrees from this equation and found out that x plus y equals to 360 degrees plus 180 degrees is 180 degrees. So x plus y equals to 180 degrees. In the next step, I presented to you rule 30, and we implemented rule 30 in our drawing. I put again on rule 30, according to rule 30, center angles that subtend on equal chords are equal to each other. In the circle, this is center angle COD that subtend on chord CD. The size of center angle COD is alpha. Likewise, we have center angle AOB that subtend on chord AB. The size of center angle AOB is beta. According to this rule 30, if chord AB equals to chord CD, then those two center angles must be equal to each other and their sizes. So if AB equals to CD, then alpha equals to beta. That is to say, if two center angles subtend on equal arcs, they must be equal to each other and their sizes. So if AB equals to CD, then those two center angles must be equal to each other and their sizes. That is to say, alpha equals to beta. So according to rule 30, if center angles subtend on equal arcs, they must be equal to each other and their sizes. So we can implement rule 30 in our drawing. In our drawing, we have center angle QOB, and it equals to x degrees in its size, and it subtends on chord PQ, this is equals to 6 units in its length. Likewise, we have center angle AOB, this is equals to y degrees in its size, and center angle AOB subtend on arc AB, that is equals to 8 units in its size. So I copy this circle in a new page, and I copied also center angle AOB. Again. This circle is identical to our original circle, and this is center angle AOB. This is a copy from the original drawing. This is equals to 90 degrees and to y degrees in its size. And center angle AOB subtend on arc AB. This is equals to 8 units in its size. So copy this center angle with its chord from the original drawing. Then I did the construction. That is to say, from point B, I draw a chord that is equals to 6 units in its length according to my construction. Again, from point B, I draw a chord that is equals to 6 units in its length according to our construction. That is to say, chord BC equals to 6 units in its length according to my construction. And we join points O and C together by straight line. Point O is the center of the circle, so we join points O and C together by straight line. By doing this construction, we get the center triangle BOC. Center triangle BOC subtend on chord BC that is equals to 6 units in its length. And this circle is identical to our original circle. Center triangle BOC subtend on chord BC that is equals to 6 units in its length. Likewise, we have here center angle POQ that subtend on chord PQ that is equals to 6 units in its length. Therefore, because of the fact that center angle PQ subtend on chord PQ that is equals to 6 units in its length, and we have here center angle BOQ that subtend on chord BC that is also equals to 6 units in its length. So those two center angles subtend on equal chords because BC equals to QP equals to 6, and therefore they must be equal to each other in their sizes. But the size of this center angle BOQ is x, therefore the size of this center angle BOC must be equal to x degrees according to rule 30. Okay, so in total we can find out that the big angle AOC equals to x plus y degrees in its size. Again, the big angle AOC equals to x plus y degrees in its size. But we already found out that angle x plus y equals to 180 degrees. So the big angle AOC that is equals to x plus y is 180 degrees. So we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore AC is a straight line. But AC is a straight line that touches the circle 2 points, A and C. Therefore AC is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore AC is the diameter of the circle. Here we can implement rule 7 in our drawing. In our drawing we have perpendicular ABC that subtend on the diameter of the circle, and according to rule 7, any perpendicular that subtend on the diameter of the circle must be equal to 90 degrees in size. Therefore, according to rule 7, perpendicular ABC must be equal to 90 degrees in its size. So in the next step, I copy the right triangle ABC in a new page and implemented the parallelogram on this right triangle ABC. Side AB equals to 8 units in its length according to what is given as the question. Side BC equals to 6 units in its length according to our construction. And AC is the diameter of this circle according to rule 30. Because of the fact that AC is a chord that passes from the center of the circle, therefore it must be the diameter of the circle. So actually, this is the right triangle ABC, this is a copy from the original drawing. This right triangle ABC, AC squared, that is the square they produce, equals to AB squared plus BC squared. AC is the missing side, so it is 6, so it is AC squared equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So in total AC squared equals to 64 plus 36. 64 plus 36 is 100, so AC squared equals to 100. Here we took out of this equation and found out that AC, the diameter AC equals to the square root of 100, that is 10. So the diameter AC is 10, therefore the radius must be equal to half of it, that is 5. So the radius of this circle R equals to 5 units. Our task is to find out the area of the circle. Note that the area of any circle is equal to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. R is 5, therefore r squared is 5 squared, that is 25. So in total, the area of our circle must be equal to either 25 pi square units in size, or in terms of numbers, the area of this circle must be equal to 78.54 square units in size. So we finish with the first method. In the next step, I presented to you how to find out the area of this circle according to the second method. In the second method, we used with some of the fields that we already found out in the first method. We already found out in the first method that those triangles are both equal to alpha. Those are vertex triangles that are equal to each other. Those triangles are both equal to 90 degrees. So in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right triangle P and Q, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you prove that all the three angles of this right triangle A and B are corresponding equal to all those three angles in this right triangle P and Q, therefore those two right triangles are similar to each other according to angle similarity rule. So if you found out that the right triangle A and B is similar, this is the sum of similar to the right triangle P and Q according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle A and B, or side PQ of the right triangle P and Q, is equal to side AM of the right triangle A and B, or side PM of the right triangle P and Q. It is also equal to side VM of the right triangle A and B, or side MQ of the right triangle PMQ. Repeat again. We derive that AB over PQ equals to AM over PM equals to MB over MQ. AB is 8, PQ is 6, so it is equal to AM over PM. Here we divided both the numerator and the denominator of this number by 2. 8 over 2 is 4, and 6 over 2 is 3. So 3/3 equals to AM over PM. We multiplied both the numerator and the denominator of this number by A. And we found out that 4A over 3A equals to AM over PM. It means that if AM equals to 4A, then PM must be equal to 3A. But again, this equation means that if AM equals to 4A, then PM must be equal to 3A. But again, if AM equals to 4A, then PM equals to 3A. So AM equals to 4A, and therefore PM must be equal to 3A. Likewise, those two sides of the equation also equal to each other. AB over PQ is 4/1. This is equal to MB over MQ. So 4/1 equals to MB over MQ. When we multiply this equation, this number, both the numerator and the denominator of this number by B, and found out that 4b over 3b equals to mb over mq. This equation means that if mb equals to 4b, then mq must be equal to 3b. Again, if mb equals to 4b, then mq must be equal to 3b. So if mb equals to 4b, then mq must be equal to 3b. So we have here PB is a chord. PB is a chord, this is absolutely a straight line. So if we focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. That says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PB at point M? We have this angle that is the right angle plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees according to rule 3. So we join points B and Q together by straight line. In this way, created the right triangle BMQ. So copy the right triangle BMQ in an equation. We implemented the Pythagoras theorem. This right triangle BMQ. So actually, this is the right triangle BMQ. There's a copy from the original drawing. In this right triangle BMQ, BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. BQ is the missing side, so we leave this is this, so it is BQ squared equals to MB squared. MB is 4B, therefore MB squared is 4B squared, that is 16B squared, plus QM squared. QM is 3B, therefore QM squared is 3B squared, that is 9B squared. 16B squared plus 9B squared is 25B squared. So in total, we actually found out that BQ squared equals to 25B squared. So here we have, we took out of this equation and found out that BQ equals to the square root of 25, that is 5, times the square root of B squared, that is B. So in total, BQ equals to 5B units in its length. This is line 7 BQ, that is equals to 5 units in its length. In the next step, we calculated the area of this triangle ABQ in two different ways, and then we created an equation that said the area of triangle ABQ according to the first calculation must be equal to the area of triangle ABQ according to the second calculation. According to the first calculation, the area of triangle ABQ equals to the base of the triangle, that is AQ, times the height to the base, that is MB, over 2. According to the first calculation, the area of triangle ABQ equals to the base AQ times the height to the base, that is BM, over 2. And it must be equal to the area of triangle ABQ according to the second calculation. According to the second calculation, the area of triangle ABQ is equals to AB times BQ times sinus angle ABQ over 2. So we have the area of triangle ABQ is equals to AB times BQ times sinus angle ABQ over 2. We have to find out the value of sinus angle ABQ, and in order to find out the value of sinus angle ABQ, we will implement the law of sines in this triangle ABQ. According to the law of sines, first of all, the law of sines is true in any triangle. This is a triangle ABC that could be any triangle. Side AB equals to 3 units in its length, side AC equals to B units in its length, and side BC equals to A units in its length. This is angle alpha, this is angle beta, and this is angle gamma. According to the law of sines, the following equation is true: that A over sinus alpha equals to B over sinus beta equals to C over sinus gamma, and it is equals to 2R. 2R is the diameter of the circle that blocks the triangle ABC. We can definitely implement the law of sines in our drawing, because in our drawing we have triangle ABQ. that is blocked by this circle. And therefore, according to the law of sines, the following equation will be true, that AQ over sinus angle ABQ equals to 2R, and 2R is the diameter of this circle that blocks triangle ABQ. Repeat again, according to the law of sines, the following equation will be true, that AB over sinus angle ABQ equals to 2R, and 2R is the diameter of the circle that blocks triangle ABQ. Here we multiplied this equation by sinus angle ABQ, and then we divided by 2R simultaneously, and we found out that sinus angle ABQ equals to AQ over 2R. Now we can substitute sinus angle ABQ in this equation, here, by AQ over 2R. We did it, and we found out that AQ minus BM over 2 equals to AB times BQ over 2, and sinus angle ABQ equals to AQ over 2R. Here we have 2 on both sides of this equation, so 2 will get cancelled. We have AQ on both sides of this equation, so AQ will also get cancelled. After we cancel those two expressions, in this side of the equation we left only with BM. This is equals to AB times BQ over 2R. So BM, here we multiplied this equation by R, and we divided by BM simultaneously, and found out actually that R equals to AB times BQ over 2 times BM. So R equals to AB. AB is 8 times BQ. BQ is 5B over 2 times MB. MB is 4B. Repeat again. AB is 8, BQ is 5B, and MB is 4B. So in total we should find out that R equals to 8 times 5B over 2 times 4B. We have 8 in the numerator and 8 in the denominator. Why? Because 2 times 4 is 8. So 8 will cancel with 2 times 4. And B will cancel with B. We have B in the numerator and the denominator, so B will get cancelled, and we left only with 5. So in total we should find out that the radius of this circle R equals to 5 units. Our test is to find out the area of this circle. So actually, the area of any circle is equal to pi times the radius of the circle squared. And therefore the area of this circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So in total, the area of this circle must be equal to pi R squared. But R is 5. Therefore, R squared is 5 squared, it is 25. So in total, in both methods, we found out that the area of this circle, that is the area that we are looking for in this question, it is equal to either 25 pi square units in size. So in terms of numbers, the area of this circle is equal to 50. Actually found out that the area of this circle equals to either 25 pi square units in size, or in terms of numbers, it is equals to 78.54 square units in size. I repeat again. Actually found out in both methods that the area of this circle equals to either 25 pi square units in size. So in terms of numbers, it is equals to 78.54 square units in size. Okay, thank you very much.